March 1941, at the Naval Yard on Mare Island in Vallejo, California, a welder named Edward Nelson worked under dim lights inside a submarine assembly bay. Earning $11 a day, he spent breaks jotting down notes in a battered notebook, venting his irritation. Supervisors pushed for faster output, yet ignored the improvement he believed could solve their delays. That day, moving through the maze of platforms beneath an unfinished deck, he watched a crew spend an entire shift installing a single section of wooden planking. The sight left him convinced the system was outdated. Inside the vessel's compartments, large scaffolds filled the cramped spaces below each deck. Workers below tightened nuts onto bolts pushed through the planks from above, contorting themselves in narrow areas for hours. The process was slow and labor-intensive, but it had changed little in decades. Meanwhile, tensions in the Pacific were rising, and time was becoming a critical resource. The yard, soon to be one of the Navy's busiest, still relied on methods inherited from an earlier era. Nelson was 36, born in California, and had learned his trade through years in machine shops across the state. 15 years of hands-on experience had taught him the behavior of metal, the flow of current, and the importance of practical solutions. Unknown to his supervisors, he had already devised a fix for the inefficiencies he saw daily. What he did not realize was that the idea dismissed by his superiors would eventually save the Navy tens of millions of labor hours and permanently alter shipbuilding practices. By mid-March 1941, months before the attack on Pearl Harbor, time, a number that would surge dramatically within a few years, Nelson was one of those workers assigned to welding submarine hulls and internal structures. He was efficient and skilled, yet increasingly frustrated by what he saw as needless delays. The installation of wooden decks on submarines, destroyers, and carriers alike was particularly inefficient. Wood was used for traction, noise reduction, insulation, and easier repair in case of fire. However, attaching those planks required a complex, multi-stage procedure that consumed both manpower and time. Workers first drilled and countersunk holes in the planks so bolt heads would sit flush. The boards were then placed on the steel framework. Next came the most difficult stage, building scaffolding beneath the deck to reach the underside. Teams above and below coordinated to push bolts through the wood and steel, while others underneath threaded and tightened nuts. Once secured, workers on top plugged the countersunk holes with wood. This sequence had to be repeated thousands of times for a single vessel. On submarines, crews of a dozen or more men could spend nearly a week completing deck installation. Building and removing scaffolding alone required days. Nelson had carried out the task many times, often in spaces barely high enough to stand. The physical strain was constant, but what troubled him most was the broader impact. Production schedules were already tight, and war seemed increasingly likely. Every delay meant fewer vessels ready for service. Over months of routine welding, Nelson considered alternatives. Stud-welding was not entirely new. It existed in limited use for flat, horizontal surfaces, where loose flux powder helped fuse a stud to steel using an electrical arc. However, the method failed on vertical or overhead surfaces because the flux would fall away. Naval construction required welding at every angle, a challenge that had stumped engineers for years. Nelson's insight was simple: enclose the flux inside a small ceramic cap fixed to the end of the stud. With the flux contained, welding could be performed in any position. He sketched a handheld tool with a spring mechanism to press the stud against the steel, a trigger to create the arc, and a disposable ceramic cap. Each stud could be attached in less than a second. A single worker could complete in minutes what previously required hours. Confident in the idea, he presented it to a Navy lieutenant who supervised the shop. The meeting was brief. The officer glanced at the drawings and dismissed the proposal, citing established procedures and existing specifications. Nelson was told plainly that if he preferred welding to overseeing bolt work, he should remain in his assigned role. Unwilling to drop the matter, he sought out the shipyard's senior welding engineer, Hartwell, a civilian contractor. Nelson laid out his argument. The method he envisioned would cut hours from each build, reduce manpower, and eliminate the need for expensive scaffolding. Hartwell listened with courtesy, but showed little enthusiasm. He explained that many capable engineers had tried for years to solve the same issue. If a simple fix existed, it would already be in use. Responsibility was to build vessels exactly as specified, and Nelson's job was to complete the welding tasks assigned to him. Frustrated but persistent, Nelson drafted a formal letter to the shipyard commander, Captain Thomas Withers. In careful language, he described inefficiencies in the current process, outlined his stud welding concept, and estimated potential savings in time and cost. He submitted the proposal through the proper internal channels. 3 weeks later, a standard reply arrived. It thanked him for his interest in improving efficiency and noted that technical suggestions were reviewed by the Bureau of Ships Engineering Board. His idea had been forwarded, but evaluation typically required 18 to 24 months. He would be informed if further study was authorized. To Nelson, that timeline felt useless in wartime. By then, the conflict might already be decided. He discarded the letter in anger and made a decisive choice. If the Navy would not test his idea, he would do it himself. In the garage behind his small Vallejo home, Nelson began gathering scrap steel and equipment. His wife, Emma, worried that his side project might jeopardize his job. Nelson insisted the work would ultimately benefit the Navy, even if officials did not yet recognize it. Evenings and weekends were spent building a prototype stud welding gun. The first version was rough but workable, a pistol-style grip, a spring mechanism to hold the stud in place, an electrical trigger linked to a power source, and a simple system for reloading. Each weld took less than a second, produced strong joints, and required access from only one side of the surface. During lunch breaks, he showed the tool to other welders, who quickly recognized its potential. Some urged him to present it again to supervisors. Nelson declined. He had already tried. One co-worker suggested he leave and market the invention independently. The idea was new to him. He had experience with welding, not business. He lacked capital, manufacturing space, and commercial contacts. Still, the suggestion began to seem practical. If the Navy would not adopt the device, private shipyards might. Along the West Coast, facilities were expanding rapidly and facing labor shortages. On June 20, 1941, Nelson resigned from the Mare Island Naval Shipyard. His supervisor advised him not to abandon stable employment for an unproven invention, but Nelson was determined. He intended to manufacture welding guns and believed that eventually the Navy would return as a customer. He left with little money, a garage workshop, and confidence in his design. On July 1, 1941, he formed the Nelson Specialty Welding Equipment Corporation. To fund production, he secured a $95,000 loan from the Reconstruction Finance Corporation, a government agency that supported small businesses. With the funds, he rented a modest workspace in Vallejo and began building stud welding equipment. Early months were difficult. He had no established customers or distribution network. He visited machine shops and small fabrication firms, demonstrating the tool and explaining its advantages. Many remained doubtful. A few agreed to try it. Orders arrived slowly at first. The country accelerated production. Kaiser's facilities increased output of Liberty ships, and naval yards received emergency orders for submarines and other vessels. In this new environment, technologies that could save time and labor suddenly carried far greater importance. As wartime production intensified, private shipbuilders such as Bethlehem Steel and other major yards shifted to non-stop operations, running crews in continuous rotations. Despite the urgency, every yard confronted the same bottleneck. Existing shipbuilding techniques were too slow and required too much labor. The industry needed a faster way to attach components to steel hulls and decks. Within weeks, Ted Nelson's workshop began receiving calls from purchasing agents who had recently dismissed his stud welding system. Now, faced with mounting pressure to accelerate construction, they urgently wanted his equipment. Kaiser's shipyards placed a large order for welding guns and thousands of studs. Bethlehem Steel followed with its own request. Even Mare Island Naval Shipyard, where Nelson's proposal had been rejected earlier, submitted a sizable requisition handled by his former supervisor. The order came without apology or recognition, only a brief directive for rapid delivery. By January 1942, less than a month after Pearl Harbor, Nelson's small operation was overwhelmed. Demand for his tools exceeded his production capacity. Realizing he needed larger facilities and more workers, he leased a bigger site in San Leandro, south of Oakland. The building was modest and isolated, surrounded by farmland, but it offered space and electrical capacity for expansion. Assembly lines produced dozens of welding guns daily, and stud output reached the thousands. Soon, nearly every major West Coast shipyard relied on Nelson's system. Reports from the field showed dramatic efficiency gains. Tasks that once required large crews and nearly a week to complete could now be finished in a single day by a fraction of the workers. Eliminating scaffolding saved additional time and freed labor for other priorities. The welded studs also proved stronger than traditional bolted connections and simplified maintenance by allowing deck planks to be removed and replaced more easily. Submarine construction benefited especially. At Mare Island, production speed improved steadily as new methods were adopted. Stud welding was only one of several advances, but it played a key role. By mid-1942, the technique was used not just for deck installations, but for pipe supports, cable brackets, equipment mounts, and bulkhead fittings. Any application requiring fast, reliable attachment to steel. Initially skeptical, the Navy's engineering divisions began formal evaluations of Nelson's process. Tests examined strength, durability, and failure patterns. Results confirmed that the welds were not only quicker to install, but also more dependable than conventional methods. In November 1942, less than a year after Nelson had left his modest welding job, a delegation of Navy officers visited his San Leandro plant without notice. Earlier proposal had not been properly reviewed and apologized for the oversight, noting that independent development had ultimately sped deployment, more than standard procurement channels might have allowed. As the war continued, demand kept rising. In March 1943, Nelson opened a second plant in Camden, New Jersey, to supply East Coast shipyards. By mid-1943, his company employed over 400 people and generated several $1 million in annual revenue. Despite the growth, he maintained long workdays on the factory floor and paid himself a modest salary, reinvesting profits into expansion and equipment. The broader impact of stud welding was immense. Early estimates of millions of labor hours saved grew as the method became standard across naval construction. It was used on submarines, aircraft carriers, battleships, cruisers, destroyers, and numerous smaller vessels. Large carriers required tens of thousands of studs each, while other ship classes incorporated the system throughout their structures. Yet submarine production saw the most striking improvements, with several yards achieving faster build times as efficiency measures accumulated. What began as a rejected proposal had evolved into a widely adopted innovation that significantly accelerated wartime shipbuilding. Portsmouth Naval Shipyard's wartime productivity rested on several technological and organizational advances, yet one of the most decisive was the widespread use of stud welding. 4 submarines launched within hours marked a record unmatched by any other yard. During its peak year, Portsmouth completed 32 submarines, averaging roughly 1 finished boat every 11 days. Most of these were Balao-class submarines, and at Portsmouth, they typically moved from keel laying to commissioning in about 12 months, several months faster than comparable yards. Other facilities also contributed significantly. The Electric Boat Company in Groton, Connecticut, produced 74 submarines during the war, while Manitowoc Shipbuilding in Wisconsin, far from the coast, built 28 boats that were sent down the Mississippi River to the Gulf of Mexico. Altogether, American shipyards delivered 203 submarines in World War II. Each one required thousands of stud-welded attachments, and every individual weld saved small amounts of labor time. When multiplied across thousands of fittings per vessel and hundreds of vessels overall, the cumulative savings became enormous. Submarines, however, represented only part of the overall output. Surface combatants and merchant vessels were built in far greater numbers. The Liberty Ship program, overseen by the U.S. Maritime Commission and largely constructed in Kaiser shipyards, produced 2,710 cargo ships. Each required roughly 5,000 to 8,000 stud-welded connections for decking, cargo equipment, defensive armament, and structural fittings. The later Victory ships followed similar practices. The scale of this production had no historical precedent. In 1943, American yards were launching as many as 3 new ships a day, about 75 per month, or 900 in a year. Could still endure rough seas and enemy action. By spring 1943, naval authorities formally recognized the importance of Nelson's contribution. On May 11th of that year, the Secretary of the Navy presented the Nelson Specialty Welding Equipment Corporation with the Army-Navy E Award for Production Excellence. Established in 1942, the award honored companies that achieved exceptional performance in both output and quality. Only a small percentage of war contractors received it. The recognition included a factory pennant and pins for all employees, awarded during a ceremony at the San Leandro plant, attended by military officials and local leaders. Workers who had labored long hours to meet demand accepted their pins with pride. Company leader Ted Nelson, dressed as he would be on the shop floor, reminded employees that their efforts were driven by necessity rather than recognition, each weld and each component contributing to the safe return of American service members. Plants that maintained high standards for 6 months after receiving the initial award earned additional stars. Nelson's company secured its first star in November 1943 and a second in May 1944. By war's end, it had received 2 E awards with stars, a distinction shared by very few manufacturers. Official citations credited the firm's technology with saving an estimated 50 million labor hours in naval construction. That figure equates to thousands of years of work by a single individual. Such savings translated directly into faster ship delivery, more submarines on patrol, more escorts protecting convoys, more carriers launching aircraft, and more landing ships delivering troops. The broader strategic consequences were impossible to measure precisely, but undeniably significant. As labor shortages grew, women entered shipyards in large numbers. While Rosie the Riveter became a symbol of the era, many women also worked as welders, operating stud welding equipment, installing deck planks, and mounting shipboard gear. Some became highly skilled specialists. Mare Island Naval Shipyard employed nearly 50,000 workers at its peak, including around 9,000 women. Kaiser yards hired hundreds of thousands overall, with women making up close to a third of the workforce. Tools that could be learned rapidly and used safely were essential, and stud welding met that need. By 1944, Allied industrial output had begun to overwhelm Axis capabilities. Innovations in manufacturing, large and small, combined to accelerate shipbuilding on a massive scale, and stud welding stood among the technologies that made this unprecedented surge possible. During the Second World War, the United States outproduced both Germany and Japan in ships, aircraft, armored vehicles, and weaponry. President Franklin D. Roosevelt famously described this enormous industrial output as the arsenal of democracy, and American factories ran at maximum capacity to sustain it. Among the countless innovations that supported this effort were Ted Nelson's stud welding guns, small components in a vast system, yet meaningful ones. In wartime, efficiency translated directly into lives preserved and campaigns won. When ships could be assembled more quickly, fleets reached combat sooner. Losses could occur. Although Japan entered the conflict with more submarines, it built only 126 during the war, while the United States completed 203. Each additional month shaved off construction schedules meant another vessel at sea sooner, extending the reach of undersea warfare. Aircraft carrier production followed a similar trajectory. In December 1941, the U.S. Navy possessed only 7 carriers. By August 1945, that number had grown to 99 across all categories. Central to this expansion were the Essex-class fleet carriers, 24 ships capable of carrying around 90 aircraft each. From mid-1943 onward, fast carrier task forces built around these vessels dominated Pacific operations. They bombarded coastal defenses, launched sustained air offensives, shielded amphibious assaults, and confronted Japanese fleets in decisive engagements. The Battle of the Philippine Sea in June 1944 illustrated the advantage. American carrier aviation destroyed more than 600 Japanese aircraft in a single confrontation. This outcome hinged on having enough carriers deployed in the right locations at the right time. Rapid construction also underpinned large-scale amphibious operations. The Normandy landings on June 6, 1944, required roughly 7,000 ships and landing craft, the largest seaborne invasion ever attempted. Such a fleet was possible only because Allied shipyards produced landing vessels in enormous numbers. After Germany's surrender in May 1945, Allied planning shifted entirely to the Pacific and the anticipated invasion of Japan, known as Operation Downfall, scheduled for November of that year. Shipyards prepared for another surge in output. However, the atomic bombings of Hiroshima and Nagasaki in August 1945 led to Japan's surrender and brought the war to an abrupt end. With peace declared on August 15, the vast American production apparatus began to slow. Military contracts were cancelled, workers were dismissed, and many shipyards shut down or converted to civilian manufacturing. Nelson's Specialty Welding Equipment Corporation, which had employed more than 400 people at its peak, suddenly faced an uncertain future as wartime demand vanished. Ted Nelson had anticipated this transition. Even during the conflict, he had considered civilian uses for stud welding. The method was not limited to naval construction. Any industry working with steel could benefit from faster attachment techniques. Construction firms, bridge builders, manufacturers of tanks and pressure vessels, and automotive companies all represented potential markets. Nelson redirected his company toward these sectors, promoting stud welding systems to fabricators and industrial clients. The post-war building boom, highways, bridges, skyscrapers, and suburban developments created steady demand for steel assembly solutions. By 1948, the company had successfully adapted to peacetime production, operating on a smaller but stable footing and continuing to refine its tools and designs. Its industrial division. Despite these transitions, the Nelson brand endured. Today, stud welding systems derived from Nelson's original ideas are produced and sold worldwide by Stanley Engineered Fastening. Modern equipment is far more advanced, featuring inverter power supplies for precise arc control and automated or robotic systems for high-volume production. Yet the core principle remains unchanged: a stud, a flux tip, a spring-loaded gun, and an electric arc that completes the weld in about a second, often without the need for scaffolding. What began as a solution to a naval construction challenge now serves countless industries. Skyscraper builders attach metal decking to structural beams with stud welds. Bridge crews secure guardrails and lighting supports the same way. Nuclear facilities use the technique for mounting cable trays and equipment. Automotive plants rely on it for grounding points and body assembly. A technology first devised in a garage to speed wartime shipbuilding has become a standard tool wherever steel structures are fabricated. The most enduring impact of Ted Nelson's invention can be seen in the preservation of historic naval vessels. One notable example is the battleship Texas, among only 7 ships that served in both World Wars. It is currently under extensive restoration at a dry dock, where corroded hull plates and worn fittings demand careful repair. The restoration team has found that contemporary Nelson stud welding tools are perfectly suited for this work, enabling the attachment of new steel plates using the same method Nelson developed 8 decades ago. Nelson's equipment allows volunteer teams to conduct welding tasks efficiently, often without needing fully certified welders for every operation. Ted Nelson lived long enough to witness his invention transform shipbuilding practices worldwide. From the first sketches in his notebook in 1941 stud welding became a standard technique in naval construction and industrial applications alike. He passed away in 1994 at the age of 89, having seen the Cold War end and the world his generation fought for evolve dramatically. The numerical impact of his work is impressive, but only part of the story. 50 million labor hours saved, 2 Army-Navy E awards, thousands of ships completed faster, and billions of studs produced. Yet these figures do not capture the human consequences: sailors who returned home because their submarines were finished on time, Marines who survived amphibious assaults thanks to available landing craft, families spared prolonged wartime separation. Nelson's true legacy lies in the lives his invention indirectly protected. He accomplished this not through weaponry, but through construction, not by destruction, but by innovation. Nelson's path was not unique in facing skepticism. History has often dismissed groundbreaking ideas. The Wright brothers were told powered flight was impossible. Henry Ford's vision of mass-produced automobiles was ridiculed. Chester Carson struggled for years to sell his xerography process. What set Nelson apart was his persistence. He did not argue with naysayers or waste time trying to persuade doubters. History: it produced 512 ships, repaired thousands more, and built 44 submarines, including California's last nuclear-powered submarine, USS Drum, launched in 1970. Parts of the yard were recognized as historical landmarks, and some structures remain preserved, including dry docks, the chapel, and industrial buildings. Visitors can still walk through these spaces, imagining the intense wartime activity as workers labored around the clock to complete submarines. A small museum now occupies the old pipe shop in Building 46, displaying tools, photographs, and artifacts from the yard's past. Though there is no dedicated monument to Nelson, and his story is known mainly among welding experts and maritime historians, he likely never sought public recognition. His focus was on solving problems, improving efficiency, and contributing to the war effort. The success of his method, its ability to save time, lives, and reshape an industry, was recognition enough. Nelson's example serves as a reminder that innovation often emerges from unexpected quarters. Breakthroughs do not always come from credentialed experts or high-tech laboratories, but from practical minds who confront problems daily. Solutions can arise in a shipyard, a garage, a hospital, or a classroom from those deemed unqualified, told to follow rules, or dismissed as pursuing the impossible. The next transformative idea may come from anyone willing to act on what they know is right, regardless of established authority or conventional wisdom. History teaches us to pay attention to those who notice problems others overlook. Yet together, they removed the need for scaffolding, sped up production, enhanced safety, improved quality, and allowed ships to be built far more efficiently at a critical time. The practical impact was enormous. One welder's innovative approach ultimately saved an estimated 50 million labor hours, equivalent to 5,700 years of work. This calculation only measures direct construction time. It does not capture the strategic advantage gained by deploying ships faster, the lives protected as submarines reached the Pacific sooner, the boost to morale from exceeding production targets, or the deterrent effect of a rapidly growing naval force. The full scope of Nelson's invention may never be completely quantified. Yet it is clear that the United States' wartime success relied as heavily on industrial ingenuity as on battlefield heroism. Soldiers, sailors, and Marines fought the battles, but it was the workers, engineers, and inventors who ensured victory. Nelson represents a larger principle. Innovation often comes from those closest to the problem. People who refuse to accept inefficiency and understand that every hour saved in production can mean lives saved on the front lines. Today, as humanity faces global challenges like climate change, dwindling resources, and aging infrastructure, the same lesson applies. Solutions will emerge not only from universities or corporate labs, but from individuals in workshops, factories, and garages who identify problems and develop practical remedies. The next transformative idea could come from someone overlooked by conventional authorities, whose inventions had a national impact, yet he remained grounded, never claiming anything beyond being a mechanic who found solutions. When asked about his accomplishments later in life, he would modestly remark that he just made a better mousetrap, emphasizing practicality over genius. The enduring lesson is clear. A single person with insight, persistence, and the determination to act can alter history. Nelson's innovations are still in use today. Every stud welding operation that benefits from his method continues his legacy. They demonstrate that meaningful improvements often emerge when someone questions inefficiency and refuses to accept no for an answer. In 1941, Nelson asked a simple yet critical question: there must be a better way. His answer contributed directly to winning a war. What questions are we asking today? And when conventional wisdom, bureaucratic rules, or skeptical critics stand in our way, will we pursue our ideas anyway? History shows that real breakthroughs rarely arise from following instructions. They come from observing a problem, understanding how to fix it, and daring to take action. Somewhere now, perhaps in a small workshop or garage, another innovator is sketching an idea dismissed as impossible. If history is any guide, they may just be the next Ted Nelson.